That's getting easier and easier with no one showing up till fucking 30 minutes till. Pedro's not even here today online. I just sit here chilling. I'm not lecturing to a goddamn empty room. I refuse.
Yeah, yeah.
There's a line. If you guys don't want to show up to class, fuck it. I ain't teaching. All right, math 335. A little bit of review for our test on Wednesday. And we'll focus on the latest stuff, the 2.7, 2.8 stuff. I'm off screen. So in 2.7, we had doing some basic graphs. And I really want to like hit kind of hard the a times f of x minus h plus k shifts the center from 0, 0 to hk. All of the things work on, all the equations work on this. Even something as simple as line. We're going to do y equals 3 times x minus 1 minus 2. And we're going to take a look at y equals 3 times x minus 2 plus 1. Now, both of them look like an x minus h plus k. With an a in front. So let's take a look at y equals 3x. If we, that's like without the hk, that's what we have. If y equals 3x. Okay, if I stick in x equals 0, I get y equals 0. So we have a point at the origin. And then if we look at this as m, which is rise over run, m equals 3 over 1. So I can go up 3 and right 1, up 3 and right 1. Or down 3 and left 1. Now, let's look at these other two graphs. So 4 left and right. I don't know what I'm going to need. 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I've got x and y on each of these. So here we're gonna do, this is y equals 3 times x minus 1 minus 2. If I match it up as an h and a k, h equals 1, k equals -2. So I'm gonna have a point at 1, -2. So I shift it over to 1, -2. You do the opposite sign of the one that's inside and the same sign as the one that's outside. Then we're gonna do our rise over run here. Then use m equals 3 over 1. So 1, 2, 3, right 1. 1, 2, 3, right 1. 1, 2, 3, right 1. Go down 3 and left 1. Pause before I do the other line. The key here was to start at 1, -2 rather than 0, 0, treating it like our vertex or center. Right, if we do the other one, we match up the components. H, -h equals -2. This is an easy way of doing it. You can just set these two equal to each other. And then solve for h. H equals +2. K equals 1. So I'm going to move my point to 2, 1. And then we'll do our rise over run from there. In fact, both of these lines, if we had distributed the 3 and cleaned up in mx plus b form, y equals 3x minus 5 for both of them. They're both the same line. But we're able to do that vertex thing or that HK thing. And this is gonna keep coming up throughout the semester. As we graph each new topic, you're gonna see this HK shift. The HK is the biggest takeaway.
So the Y interval or where it goes through the Y axis, it's always gonna be equal on both equations.
What do you mean?
Because like on the first one, it went through at -5, right?
Yeah, they both actually go through -5.
Yeah. Is it always gonna be like that?
Well, for this equation. If I have something different, it's not. If you were to clean it up and put it in this form and you see it like this tells you where it's crossing the y-axis.
Yeah, that -5 tells.
So if this was +3, it would cross up here.
Yeah, right. But is it just coincidence that they both?
It was designed to both be the same. I wanted to show you having the line can be written two different ways. The normal way you would do it is this. But I wanted to show that even the idea of the HK applies to lines. When we scale it to something like a quadratic function, y equals x squared. We have one, there's something at 0, 0. Then you go right 1, up 1, and left 1, up 1. Then right 2, up 4. So 0, 0, 1, 1, and 2, 4 are your movements, any of the direction. We can shift this though. If I do like x plus 3 squared minus 2. This compares to x minus h squared plus k. So negative h equals +3 by comparing these two.
Yeah.
So h equals -3 and k equals -2. We can move 0, 0 to -3, -2. And then do this same thing, then this from there. From HK. So if I were to do that, -3, -2 is down over here. We'll put more of this is on that. I guess you need to go down as far. It should go more to the left though. X, Y. I'm moving my center to -3, -2. And from here, I'm going to go right 1, up 1, and left 1, up 1. And then right 2, up 4. Left 2, up 4. In fact, today in the regular lecture, yeah. We're gonna find these points. We're gonna learn how to find those points and this point and do the graph a little bit quicker. But when it's already written like this is super fucking quick. When it's written in another form where it's all multiplied out and you have ax squared plus bx plus c, it's a little longer. Something else we did, we looked at composition of functions. Log x equals f of g, oops, f of g of x. So if f of x is square root of x minus 1, and g of x is x squared minus 2x minus 3x. Fuck it, let's go minus 3x. When we do f of g of x, we're really taking x squared minus 3x and putting it into f. Which means everywhere I see an x in f of x, I'm replacing it with that g of x, and I'm going to do it in parentheses. Here, the parentheses don't help, but sometimes they do, like if you're squaring or something like that. Let's see, I think I'm going to change that. Let's make this -4 in here, x minus 4. Easier on the demonstration. That is the composition of f of g of x. Log x is square root of x squared minus 3x minus 4. Now, what is the domain? Where's my blue pen? I don't know what my blue pen is.
That's right. Yeah.
Look at the domain of this real quick. So the domain of f of x is, we have x minus 4, we want x minus 4 to be non-negative. We don't want no negatives in the radical. So f of x gives us x is greater than or equal to 4. G of x is all real numbers. Again, infinity to infinity. When we do the composite, the f of g of x, both restrictions hold as is. Both domain restrictions hold. But the composition may introduce more. So fog x was x squared minus 3x minus 4. We want that to be greater than or equal to 0 also. This factors into x minus 4 and x plus 1. So if we do a little number line, we can see where that is. We got a solid point at -1 and a solid point at 4. So And then we check our points. Let's try 0 here. We'll try 0. We'll try like -10 and +10. We just need to see the sun. We did this, so it was been a little while, but we did this. We just need to see the sun. -10 -4. And -10 + 1. This is a negative times a negative, makes this region positive. If we stick in 0, we just have -4 × 1. That's definitely a negative number. And if we stick in 10, we have 10 - 4 times 10 + 1. Those are both positive, so this is a positive region. See how I want to say this last part. When we do the composite, this is actually the new setup. So those are the positive regions. The restrictions we need, the domain restrictions we need. Are for f of g of x. You need g of x's and f of g of x's. F of x domain gets altered by the g of x. So we're looking for the overlap of g of x, which is all real numbers, and this. So the domain here is going to be -∞ to -10 in union with 4 to infinity. By having g of x being plugged in, we've actually extended f of x domain. Now more stuff works in the new function. A little tricky. I think that's, we're already almost into the next class.